Hello and welcome to how to program. What have I called this series? Programming effectively in C++. Forgotten the name. Effective programming in C++. And the current lesson is this one, number 48. In today's lesson, since we're now pretty much purely looking at the C++ language and language extensions from C, I would like to show you another extension. As you recall, and I hope you haven't gotten confused by this, these things we've been calling classes are just structs. Okay, it's the same as struct. And I'd like to, for this lesson, I would like to use the struct keyword so we don't have to worry about public and private, all that. Everything will be public. And what I would like to talk about is something called inheritance. Now that's why this project that I've made is called Inherit. Now in C, suppose you created a struct in C called, the top one to be A, I guess so. A. Hang on a sec. Okay. A is what I want. Now I want to give this struct a member, something we'll recognize. And so I'm going to give it as a member, let's say int is too common. How about a short? SH for short. That's a 2-byte variable. Okay, now just to be sure, because this struct may not actually be of size 2, let's print out the size of the struct. Size of A equals %d size of A. Okay. And now that should print out 2, I hope. Okay, that's correct. So this is a struct which is of size 2. It's exactly, in fact, the size of its member. Now, since this struct, and in fact it's true for any struct, contains a single member, in memory, all this thing looks like, if I say I created one here on the stack, okay, and I'll let this equal to be something in hex, so we'll recognize it. 2, 3, 4, 5. Not very likely to find that in memory. If I run up to here, let's step over that. Okay, now what I want is to locate A. Now I can do that in the watch window. A apparently is at this spot in memory. I need a memory window. Which I don't want there. I would like to put it here. Okay. And I want to take this address. Okay. Now, That here is the address where A is stored. And as you can see in the backwards line, it's reading 2345. So in fact, this struct and its member and the member sh are at exactly the same address. So I could, in theory, if I liked, I could say %b is this, and I could just interpret A as if it were a pointer to a short. Oops. Address of A. Okay. And then dereference that. I don't know if you can specify short, but it'll be pushed onto the stack as a long value. And that should print out 2, 3, 4, 5. Let's put this in hex. This would just prepend zeros to our hex output. Okay, 2, 3, 4, 5. Make it look more like hex. Let's add carriage return. Away. Okay. So I've figured out basically a dot remember, this is little a really. Now that would also be true if this was private. It'll compile. Yeah, it should compile. No. Oh, I can't set it. I'll make a constructor. So this A automatically becomes 2, 3, 4, 5 in this case. Now, see, we've had a look at A's private data just by knowing the fact of the layout of the structure. In fact, A is, in every sense of the word, a short, because that's all it has as a member. The struct itself doesn't add any additional data to the object. All a struct tells you is about the way things are laid out. Now that's not always the case. Sometimes, because of the way the way things are aligned in memory, you might declare just one single character, but the actual size of the struct may be 2 instead, even though the extra character is ignored. I'm not sure how we can test that, but that's not my point here anyway. My point here is that more important than being able to find out the data inside of A, knowing where the address of A's data is tells us where the struct is. And I'm going to want to be using that later on in order to double check some of the things that we're going to do. So keep this in mind. Alright. Next. Now that's one structure which I lost my short. I lost my shorts. one struct. Now suppose there were in the world another struct called B. And then let's let B have, in my example, I think I had a float in here. And I want something bigger. How about a double? Double's like a float, but it's a bigger float. D. Okay, that's something that has a mantissa, fractions, a decimal point, and so on. Okay. Now, here I got these two structs, and in C, if I wanted to include B in my A structure, that is, suppose I would like something of B type inside my A thing, just as I wanted a short in here. I might not want a double specifically. Maybe B has two doubles, or an array of doubles. That. I could just add a B in here. B. Okay. Now, first off, first question, what is the size of A now? Well, if we knew the size of B, then I would say that the size of A has grown by the size of B. So let's see if that's true. I'm just going to use a string here, and well, okay, not yet. Okay, so size of B is %d something, and then size of A, I should be able to write down the answer. It's got to be the previous size of A, size of a short, plus size of %d. Then in brackets, it's the size of short plus the size of B, to emphasize in our printout what's going on. Now this should be correct, and I think a double is 4 bytes, so that's 6 times 6, 24. It should be 26 if my guess is true. I'm not putting them in. So size of B and then size of A. I'm not going to do this computation. I want to see if that computation ends up being the size of A. Okay, run this. Yeah. Well, 6, so these are 8 bytes then, not 4. But still the answer should be the same. 6 times 8 is 48, so the size of A should be 48 plus the size of a short. So 48, but it's not. You see that? It's not the size of B plus the size of a short. Because short size is only 2. And the size of A comes out to 56. Now the question is, and I'm surprised as you are, I expected this to work. Why are we getting a different answer? size of B, that certainly says size of B, size of A, percent D, in which I've only put size of A, which includes one B, which is that big, and one short. Now this may be something to do with this alignment thing. So now, the next question then is, well, first, why? And second, where is A dot short? Starting from the offset, the beginning of A. Now I know that A, the address of A, oh wait, yeah, I need to make an A. I don't really need one, but this is easier. A star PA would be equal to the address of A. Now that address ought to be the address of the first double in this array of doubles. Okay, so I bet if I said double star equals the address of A dot B dot D of 0 PD, then let's see what the difference is. They should be the same. Here's the expression. Address of A equals, and we use pointer specifier, and this expression, A's member B, so if you wanted, you could say A dot B which is a B. So just to make sure that we're taking the right address, A dot B is a B, and a B contains a D, so I can say dot D, and this is an array of 6 doubles, and I can take the 0th element, and so that expression is valid. Percent P. Now I expect those to be the same. And they are. Okay. Address of A is 12FFE0, and the address of A dot B dot D of 0 is, as I explained before, the first member in the struct should give you the address of the struct. Now the question is, what about this extra 8 bytes? Well, no, 6 bytes. There are 6 extra bytes that didn't exist, that shouldn't exist. So the way to answer that question would be to find out where this is with respect to the address of A. So let's print out. What I want to find out is the address of A dot short equals percent %P for pointer. Okay. Now I want to compare that with the address of A plus the size of B. I'm going to have to do a cast to make sure it adds byte-wise. That's okay. So I mean to say at offset B. So we can work that one out. And those should not be the same. There should be a difference of 6. Now this is another address, and I want the difference. The diff is, and put that in integer format. Now we got to figure out what all these things are. Well, this part's easy. Now, again, this is the address of A. Now I have to cast that as a pointer to a single character thing. So we could call it a car star if you like. Address of A plus stars of B. Okay. So as long as I've cast this as a byte of size byte, it's going to add to this value this count. It's not going to add this number in terms of A's, it's going to just add bytes. Now I can recast this back as a pointer. I don't even have to, because it's going to be interpreted as a pointer according to the format string. And now we want the difference. I want to take this value, I want to take this value and subtract this, which I assume doesn't go all the way up to A short. So I want to take this value and turn this into an int and subtract address of A's short. This value. Put it on a separate line. Okay, and I also want to turn that into an int. Now, how about my brackets? Says that I'm okay. So that's an int. I can subtract an int. And if I've done this correctly, which I may or may not have, the answer to that difference should be 6. But I get 0. Let's see now. I got too much extra stuff. The address of the short is 12ff blah blah blah, and if I add 48 to that, I should get this, and the difference it certainly adds up to A. Now, how come? Now I gotta pause this and try and figure out where I made a mistake. Okay, I think I understand now. It's correct as far as figuring out where the short is, and that is at offset B. Okay, but the structure itself has an extra 6 bytes. So if I expected this structure, if you want to draw a picture of it, it would look like this. So you have six doubles. That's 6. And then a short. And then 6 wasted bytes at the end. And that probably has to do with the an alignment thing. So our structure, as it stands, is correctly packed together, but we're probably using an 8-byte alignment default. Let's see what the struct member struct alignment. I've completely gone beyond the point of what this thing was supposed to be. Let's see now. Struct member alignment. Yes, default. Now let's just change this. Well, we can change the default, or we can use a pragma directive. But let's just change the. Well, let's try the directive first. Now there's a directive, which goes like this. Pragma pack, and then you say push, and then that saves the current packing alignment value on the compiler's stack, and I want to change the packing value to 1. And then to bring it back to its default, you just pop. This is a push and pop used by the compiler. Now I'm going to print all these things out again. And there somewhere. Let's not worry about that just yet. Oh, here's an error. Okay. Now, alright, now forgetting about this part, go back to where we started. This one should work. There, that's correct. And actually I added in the calculation of this sum to double check. And now by changing the default alignment, I don't get the extra 6 wasted bytes. Well, they're not wasted. There's a reason why the alignments are the way they are. If we align by 4, let's see, 48, well, it's going to give us 2 extra bytes, I would assume, because we won't be a multiple of 4. Yeah, 2 extra bytes. So the default happens to be 8. Alright, sorry for that diversion. Let me see how much I wasted on. Oh, pretty much my whole time of the lesson. Okay, well, what I want to talk about, and what I'm going to get to and I'm going to start on it right away. So I'll add to the head of this video a message that you can skip it. I'm going to show you that there's a way in C++ to include another struct within your struct, but without having to give it a name. Okay, so you